Okay, so here's our second series of lectures for Module 2, and we're going to be talking about equilibrium in lots of different ways in this module, and we're going to start out by talking about something called translational equilibrium, okay? And when we talk about translational equilibrium, what we're meaning is the motion of its center of mass, okay? Is the center of mass, how is it moving? Is it moving and not speeding up or slowing down? Maybe it's still. If it is moving, it has to keep moving in a straight line, okay? So if it's not moving, if it's moving but at a constant speed and a constant direction, then it can be in what we call translational equilibrium. All right, so this means that the motion is not going to change. All right, so its motion is not going to change where its position, how the position is evolving. Okay, so what we'll do here, I'm going to break this into a series of 4 lectures for you. And so first we're going to talk about things in the abstract. Then we're going to look at some specific examples of different situations that follow. Okay, so we're going to have 1, 2, 3, 4 videos in this particular series. So take a look here at these different blocks, okay, A, B, C, D, E, and F. And these blocks, we want to look at them, and they've got some forces acting on them. So they're getting pulled in different ways by different forces. Now, some of these blocks could be in equilibrium. Since we don't have any numbers, we don't really know for sure. But they might appear to be in equilibrium. All right. Others are obviously not in equilibrium. So what I want you to do, I want you to pause the video, look at each one of these, A, B, C, D, E, and F, and try to figure out which one of these might be in equilibrium and which ones are obviously not in equilibrium, okay? So give it a pause, see what your predictions are. Okay, so let's start with A. Okay, now we've got one in there at an angle, so there's a force directly to the left and then up and to the right. Now, what we need to do is we need to break the one that's on a diagonal into horizontal and vertical components so that we can compare it more easily. Okay, and so what we're going to have here is we're going to have a component here and a component here. Okay, now it is possible that this component will cancel out this one, that those could be equal and opposite. That sure could happen. All right, however, there's no downward force to match the upward force. And so block A is clearly not in equilibrium. Okay. Let's look at block B. Okay. Block B has an upward force and a downward force. However, the upward force is much larger. And so clearly block B, there's no way it could be in equilibrium. Unless it's just a really terrible drawing for some reason. Okay, let's look at block C. Okay, so again, what we want to do, the one that's on a diagonal, we want to break it into some components. Oops, that's the wrong device. Okay, so I got one here, and I got one here. Just like this. And yeah, you can see right away, okay, there is no way. Whoops, that is not the right one. There is no way that this guy is going to offset that, okay? And there's no way that this vertical part is going to offset that either, okay? So C cannot be in equilibrium. There's no way about that one. Okay, let's look at E. Okay, E, we've got a force to the left. We've got a force to the right. They look like they're approximately the same. They look like they're approximately equal and opposite. And so on this one, I think we could say, yes, this looks like it could be in equilibrium. We don't really know until we hit some numbers, but our best guess at the moment is that it is. Okay, let's look at D. Okay, so D, All right, we've got an upward force, a leftward force, and another diagonal. So we need to take that diagonal and we need to break it into horizontal and vertical bits. So we've got a horizontal bit here and a vertical bit there, okay? So, what do you think about that? That looks kind of promising. That really looks like this component to the right could match this force to the left. And it looks like this component downward could match this one upward right here, okay? So I'm going to say, as far as we know right now, since we don't have any numbers, I'm going to say that sure looks like it could be in equilibrium, okay? All right, now let's move over to F. Now in F, we've got two diagonals, and so we want to start off by putting them in horizontal and vertical components. Okay, hopefully you're getting in the sense that if you've got something on a diagonal, you need to just automatically convert it to its horizontal and vertical components. So we've got this here, and we've got this here. Then we're going to have this and this. Okay, so let's check it out. I don't have a good feeling about it. I mean, this component looks like it could offset that component. It's a possibility anyway. We can't immediately rule it out. However, if we start to look at what's happening horizontally, we only have this, which maybe is offset by that, but then we've got this whole thing here left over. And so clearly F is not going to be in equilibrium. Okay? All right, so let's take a look at a different scenario. And how come my picture is screwed up there? Okay. Well, my picture's messed up just a little bit. But I think we're just going to have to kind of go with it here. So I have a block here, and I've got a force here, which is 50. And what we're trying to do is figure out what are we going to need over here to put that in equilibrium. And it's pretty easy to see. If we've got 50 pushing to the right, we need 50 pushing to the left in order to make this thing work out. Okay, so that's what we're going to have there. Now there's one down here. Okay. It also has a 50 pushing here. And we can see we've got two forces pushing to the left. If one of them is 30, then the other one obviously is going to have to be a 20. Okay, so again, we get 50 one way and we get 50 to counter it. Okay, this one here is a little bit different. If we look at our horizontal forces, we got a 40 and a 30 both to the right. And so that means total to the left, we're going to have 70 there. Okay. Now, from below, we have 100. From above, we've got two forces that are identical. Okay. And so we get in our head, we don't even have to set anything up algebraically. We can know that that's going to have to be, each one of those has to be 50. A 50 there and a 50 there. And then that is going to work. And that's going to offset the 100 from below. Okay. Oh, this is not cool. Okay. Okay, so I want to look at a really simple situation here where we've got some object and a 100 Newton force from below and a 50 Newton force coming in from the left. And what are we going to need to do to keep that thing in equilibrium? Now, turns out this is exactly like the lab we did with the force tables and little rings and the strings that we put the weight on them, okay? And but I want to use this to show you basically something like a recipe, okay, for how we can proceed with problems that deal with translational equilibrium, okay? And what we want to do is we want to start out by making ourselves a free body diagram, okay? So Here's my axis. I really want to do that in white though. Okay. So here's my free body diagram. So I got X's here, Y's here, and I want to put my forces on. So I know here I've got the 100 coming up from below, and we know we've got our 50 coming over here, just like this. Now, I wanted to try to make, on my free body diagram, I want to make it reasonable in terms of how it matches the original picture, okay? So, in other words, what I'm trying to say is, I know the 50 is half of the 100, and so when I draw my 100 on there, and then I draw my 50, I want to try and make that 50 about half as long, okay? Don't kill yourself trying to do that. It's just helpful if it's approximately on par, okay? It's helpful to you. Now I have to put in my unknown force, A, okay? And so A is in here like this, and we do not know the angle theta, okay? Now, how did I know that that was theta? Well, let's draw some axes up here, okay? So here's theta. There you go. You can see how they're opposite angles like that, okay? So that's something to look for. That's how you can know which thing you're talking about there. Okay, let's get rid of these. Super quick. Okay, once I have my my drawing like that, I do need to kind of do one more thing, which is I need to realize I've got my AX on here, and I've got my AY along here. Okay, so I'm going to break that diagonal force into horizontal and vertical, just like we were doing a few minutes ago. Okay, so then we're going to come up here. I've got two equations. Okay, this guy and this guy. All right. Now, if you've had Calc 2, you recognize the giant capital sigma there. If you haven't had Calc 2, that's okay. You're not at a loss, because I'm going to tell you, these symbols right here, the capital sigma, just means you're going to add things up. Okay, you're going to add things up. All right. So if I was going to say something like this, I want to add up ends. That's like saying 1 plus 2 plus 3 plus, and I could keep going. Or I might do something where I'm going to add up values of n squared. So it'll be 1 plus 4 plus 9, that sort of thing. So the big capital sigma like that just means you're going to add stuff up, okay? And so pretty easy to deal with there. Okay, so in our context, those equations mean we're going to add up all of the x forces, all the forces in the x direction. So I look at my free body diagram, okay, and along the x direction, I've got AX and I've got the 50, okay? So the 50 is in there here, okay, and it's positive. It's in the positive x direction, so we'll leave it like that. But AX is in the negative x direction, so we add it in as a negative. So we put a minus AX, just like this. Okay, and then we're going to do the same thing with the y components. So I've got 100 up, so we put it in there as positive. And then AY is down, so it goes in there as a negative number, just like that, okay? Okay, so I need, wow, how about that? That is not what I intended to do. Okay, and so what I'm going to do then is I'm going to work my algebra. Now, when I'm doing these, I like to have both my x and y's and work them kind of simultaneously. Okay, so I'm going to sometimes when I'm doing these for you, I'll do a bunch of x stuff, then I'll go back and do a bunch of y stuff. Sometimes I may just kind of go back and forth. Okay, so on your paper when you're working these, you got to think ahead about space just a little bit, because you're used to just sort of working in a straight line down or working in a straight line going over with your math. Okay, here I need you to think about doing two columns at the same time. So make sure that you leave yourself some space. Okay, so what we're going to have here is the 50 is AX. Okay, but my AX is A cosine theta. And over here on the other side, I've got 100 is AY, but AY is A sine theta. Okay, so I know A cosine theta is 50, and I know A sine theta is 100. All right. Now, it might seem like I'm in trouble a little bit, perhaps, but realize I've got two unknowns, but I have two equations. So if I have two unknowns and I got two equations, there's a good chance I can untangle that thing to figure out both variables. Okay. All right. So the way we're going to roll with this is, favorite trick of mine is to divide things. See, I've got a sine and I've got a cosine right there. And I know that sine over cosine is going to give me a tangent. So what I'm going to do is I'm going to take my equation with my sine. So I've got 100, and that's going to be equal to A sine theta. And then I've got 50, and that's equal to A cosine theta. And I'm going to divide these two things, and I get 2 over here. My A's cancel to leave me with tangent of theta. So I know that the tangent of theta has to equal to 2. And if I run the numbers on that thing, I'm going to get that theta. I'll use my inverse tangent. I get 63.4. Okay. Now, once I know that value right there, I can take it and I can plug it in either over here or over here and solve for my value for A. I'm not going to take the time to do that. That's just basic algebra. All of you guys can do that. And we're going to find then that A turns out to be equal to 112. It's actually like 111.8, but we're dealing with 3 sig figs here, so we'll call it 112. Okay? All right. So in the next video, we're going to get to some more specific examples. All right, but I need you to have this example particularly. I need you to get your head around it as much as possible. Okay, because we've got a recipe here. Okay, so the recipe is always going to be step 1, identify the forces in our diagram. Here, our diagram, we already got that. Step 2 is do the free body diagram. Step 3 is put down the basics of what's happening in the X's and the Y's. And then step 4 is do the algebra. Okay, just like that. So we're going to do that every single time. Okay, so take that pattern, take that recipe, drill it into your brain. Okay.